Okay, so we said we gave a preview of this. So in this section, we use vectors to derive analytic descriptions of planes in R3. We also show how to solve a variety of distance problems using flat objects, points, lines, and planes. So it says a plane pi in R3 is determined uniquely by the following geometric information. You give it a point and a particular vector which is going to be normal to the plane. In other words, pi is the set of all points. So what is this plane? It's the set of all points in space such that if we take any point that's in the plane and we connect it to the point P0 with a vector, then what has to be true? That the cross product of this, or what do I want to say? That this dot this has to be 0. That means that they have to be perpendicular. So n dot this has to equal 0. Remember that the only time remember that the dot product has the cosine in it. So the cosine is going to be 0 when the angle between them is perpendicular. Since P0P, this can be written like, so if the coordinates of P are x, y, z, and the coordinates of P0 are x0, y0, z0, then P0P, so again, here's P, x, y, z, P0 is x0, y0, z0, then P0P, the vector from P0 to P, is you take x minus that, this minus that, that minus that. So this is P0, that vector. And so now we can take n, remember the coordinates of n are a, b, c, or this is the expression for n. So we take the dot product of that, and if we work this out, we get that a times this plus b times this plus c times this equals 0. And then we said that if we put all these, take a x0 and b y0 and so on, we put them all together and call it d. You can write this like this. So if we take an example, suppose we want to figure out an equation for the plane through this point with normal vector this. So it has a normal, so this is normal to the plane, and it has this point. Then we take the product of this times P0. Remember, this is P0. So we're taking n times P0, that's this, and setting it equal to 0 here, and then work it out, and we get this. So this is the equation for such a plane. The plane that goes through this point is normal to that. And as we said, any solution to this will be a point in the plane. So not only does a plane in R3 have an equation of this form, but conversely, any equation of this form must describe a plane. Moreover, it's easy to read off the components of a vector normal to the plane from such an equation. So if we look at this, where we squished all the constants into one big constant at the end here, 8, then what remains is just the 2x minus minus y and plus 4z. But where did those come from? They came from here, here, and here. So what remains is just the the coefficients here are the components of the normal vector. So the normal vector, if we look at this, we can say, oh, then the normal vector must be 2, negative 1, 4. So that's what example 2 asks you. So suppose you have this, given a plane with this equation, find a normal vector. So all you have to do is read it right here, 7, 2, negative 3, because of this previous observation. A possible normal vector is this. However, of course, any non-zero scalar multiple of this will also be normal. Algebraically, the effect of using a scalar multiple of n as a normal vector is to multiply equation 2 by such a scalar. So equation 2 here. So you can multiply this by any scalar and you get, it doesn't change anything. Okay, the problem also said identify 3 points that lie on the plane. So they're not going to use any deep insight to do this. They're just going to say, just let x and y equal 0. I'm sorry, let y and z equal 0 and solve for x. So when you do that, you get this x. So this is a point in the plane. Then let 2 of the others equal 0 and solve for the other one. So y is that, and so on. So you can do that. Okay, let's try this one. So they're going to define what they mean by a plane being vertical. So in R3. So what does it mean that a plane is vertical as opposed to horizontal? So if a plane is vertical, then its normal vector is in the horizontal direction. And they say that means that the normal vector is parallel to the xy plane. So it's parallel to the bottom plane. And if it's parallel to the xy plane, that means it has no k component. So maybe here's the xyz plane. So if we're talking about a vertical plane that goes up and down, then its normal vector is this way, which is parallel to this plane. So therefore, its normal vector has no k component. So that means its normal vector can be written in this form, having no k component, ai plus bj. But then from equation 2, here, the equation is going to be just ax minus x0 plus by minus b0 equals 0. Because only a and b are non-zero. So the normal, vertical planes have this kind of equation. So if it's not vertical, then it has this kind of equation where c is not 0. Every plane has this kind of equation, but specifically when c is not 0, it's not going to be vertical. So if the only time that it's vertical is when it looks like this, which means that c is 0. So if c is not 0, it's not vertical. Okay, let's try example 4. So they say in high school geometry, we know that a plane is determined by three points, as long as the 3 points don't lie in a straight line. So if you have 3 points and they don't lie in a straight line, then you get a plane determined by those 3 points. So we want to find the equation given 3 points. So one way to do that is to start with this equation for a plane, and then put in this value for x, y, and z, and then solve for one of the coefficients, and then do substitution and keep substituting. So they say when we put in P0, we substitute, we get this. When we put in P1, we get this. When we put in P2, we get this. and then we have the system of equations, and we can solve it. So we go through the steps. We arrive at b equals this, a equals that, and d equals this, and then we can fill in the equation like this. We get that. So that's one way to do it. But she says the second method is cleaner and more geometric. So the idea is to make use of equation 1, which is this thing here. Remember this thing? So in order to do that, we need a vertical and we need a point in the plane. So we need a vector vertical to the plane and a point in the plane. Well, we have 3 points, so we just choose one of them for the point. And then we can calculate this thing in terms of p. And we actually have, we have 3 points in the plane. So that means that, let's say, so we have 3 points, P0, P1, and P2. Then we can easily calculate 2 vectors in the plane, P1 and P2. And then if we take their cross product, we're going to get an n. So then we'll have the n, and we'll have this, and we can just write this equation, and that will generate the equation that we're looking for. It will generate the same type of equation that we got by doing substitution. So the vectors P0, P1, and P0, P2 both lie in the plane. So that means that they take their cross product, n must be perpendicular to both of them. So we do this, and we've calculated this and this as this and this, and we do their cross product, which we recall can be written as a determinant. So we put ij and k at the top. We put the vector on the left that's on the left side of the cross product in the first row, and on the right side of the cross product in the second row. And we form this determinant, and then we calculate it, and we get this. So this is the normal vector to the plane. And then choose one of the points to be P0. And so we get the normal vector times this P0P, and set it equal to 0. So the normal times this, set it equal to 0, and calculate it, and we get this, which is the same equation that we got before, apparently. Okay, let's take a look at example 5. So we're going to be given 2 planes, and then there's a line where they intersect, and we want the equation of that line, and we want to get the equation of that line in parametric form. So we're going to start out by getting the vector form. We're going to use proposition 2.1, which, remember, looks like this. So we're going to get an equation of this form. And remember where this comes from. Remember, this says the vector parametric equation for the line through the point through this point, and parallel to this vector A. So parallel to this vector looks like this, r of t. So this is r, and it depends on the t that we choose. So if we choose t to be short, then r is going to be over here. If we choose t to be bigger, then r will be over here, and so on. So r depends on t. So r of t is equal to this plus ta. So B plus TA. So we did that before, and we called it the vector parametric equation for the line through the point P and with a parallel to A. So we need to get a point, and we need to get a normal vector. We need the P0 and we need the A. So if we're given the equations of these two planes, so we're given this, and we're given this, or here, and here. So if we have that, we need to get a point first. So that's fairly simple. So we just take these two, and we want to find a point on this line of intersection. So we can just let z equal 0 for both of these, and then solve, and we get this, which we can solve. Okay, and we get a solution to that, and that's this, and this, and this. So here's our solution. That's a point on the plane. So, I'm sorry, that's a point on the line. And so we have a point on the line. Then if we're going to use the vector parametric equation for the line, we also need an A. We need a vector which is parallel to the line. So, but this line is in both planes. It's in this plane, and it's also in this plane. So this line, if it's in the first plane, must be perpendicular to a normal to this first plane. So here's the first plane. It's really hard to point it out, but here's the first plane, and then we have a normal vector in there. I'm sorry, normal vector to that plane. Okay, and then this line, because it's in this plane, must be perpendicular to this normal, because every line in the plane is perpendicular to the normal. But by the same argument, it also had this line has to be perpendicular to the normal for the second plane. So here's this normal to the second plane, and it also has to be perpendicular to that. So what is a vector? What is a vector which is both perpendicular to n, to this n? I guess I'll call this n1, and this one n2. What is a vector which is perpendicular to both n1 and n2? The cross product of n1 and n2 will be perpendicular to both of those. So, okay, what is n1 and n2? So the normal vectors to the planes are, remember we can read them off from here. So this one is 1, -2, 1. So here's 1, -2, 1. And the other one gives you this one. So if we take their cross product, we get this. So this must be our A. That's our A. And we also found a point here. So we have everything that we need for proposition 2.1. So proposition 2.1 implies that a vector parametric equation for the line is, here's the point. So that comes from here. And here's the A. Here's this thing. So we have that. And now we want to generate the standard set of parametric equations. So remember how we do that. Once we have this, we call this xi y plus yj plus zk on this side. And then on this side we have things in terms of I, j, and k. And then we just equate the left-hand side with the right-hand side. For the I parts, we equate the I parts. For j, we would equate the j parts. And for k, we equate the k parts. And we end up with these three. Okay, let's talk about parametric equations of planes. So far we have this kind of equation for a plane, or we can rewrite it like this kind of equation for a plane. And we also have this equation for a plane. So these are different forms or different possibilities for equations of planes. Now we want to talk about another way. So for this discussion, we start out assuming that the plane goes through the origin. So we're going to assume that we have two vectors, A and B, and that they both originate at the origin. So if they originate at the origin, then together they form a plane that passes through the origin. So first of all, if we have these two vectors, then we can always talk about the plane that contains those two vectors, as long as they have some point in common. If they don't have a point in common, they could be skew, in which case there's no plane that contains both of them. But if they both originate at the origin, then they have a point in common, the origin, and so there's a plane that they determine, or that passes through them, or that contains both of them. So if we want to find the, so suppose we take any other point in the plane, for example, this point, there's a way to get to this point using a combination of multiples of these two vectors. So like in this picture, we have to go out to here and then down to here. So that's take some multiple of B and then some multiple of A, and that will take you to P. So any point P in the plane can be written as a combination of a multiple of B plus a multiple of A. So we'll say T times B and S times A. So they say that to find the coordinates of a point P in P, X, Y, Z in this plane, draw a parallelogram like we have here, whose sides are parallel to A and B, and that has two opposite vertices at the origin and at P. So you have one here and one here. Then there must exist scalars S and T, so that OP can be obtained by taking a multiple of B and a multiple of A. So that's what this says here. Okay, so the plane may be described as the set of all x in R3, so a set of all vectors in R3, such that x is a combination of A and B, like this. By the way, this sometimes is called a linear combination of A and B. Now suppose that we seek to describe a general plane, pi, so not one that necessarily goes through the origin. So again, we have to assume that we have at least one point being given to us in the plane, and also that we're going to be given an A and a B that are vectors that determine the plane. So we have a point P, which is in the plane, and then we have to be given an A and a B, which are not parallel to each other, that are also in the plane. So given this information, we want to write any other point in the plane in terms of this information. So if we take any other point P in the plane, any P like this, we can say that OP from the origin to P here can be obtained by first going in the direction of C, which is going to the point P0, and then going some amount in this direction and some amount in this direction. So what we're saying is the vector OP, or the point P, equals C plus SA plus TB. So what we've shown is a vector parametric equation for the plane pi containing this point and parallel to the non-zero, non-parallel vectors A and B is this. And we see that this depends on two parameters, S and T, or we could say like two free variables, S and T, but we'll call them two parameters. Then we can, taking components, so on the left-hand side, we're going to have, and this is a point X, so it's going to have coordinates X, comma Y, comma Z, and then, it's going to be XI plus YJ plus ZK, just as before. And on this side, all this could be written in terms of I, J, and K, and then when we equate everything, we get these three equations. So this is called the parametric equations for the plane, for a plane. Parametric equations of a plane. All right? And they say you can compare this with the equation of a line, and we saw it before. Looks something like this, but here we have two parameters. Then when we were talking about a line, we had just one. So they say we need to use two parameters to describe a plane instead of a single parameter t that appears in the vector parametric equation for a line, because a plane is a two-dimensional object. So here's an example. We are given that the plane passes through this point and is parallel to these two vectors. So we can write this equation. We need the point, which is where here, this point here. So here, this point here, which is this here. The J part is missing because this is 0. And then S times A and T times B. T times B. And then we can rewrite this as like this, 3S. We collect the I components, and then the J components, and then the K components, and then we do the same thing on this side, and we equate the components, and we get this. Okay, next let's talk about distance problems. So first one is we have a line and a point, and we want the distance between them. So they say cross products and vector projections provide a convenient way to understand a range of distance problems involving lines and planes. Okay, let's see. They say what is important about these examples are the vector techniques for solving geometric problems that they exhibit, not the general formulas which may be derived from them. So emphasis here on the the fact that we're using vectors to solve these problems. Okay, so let's say the distance between a point and a line. We want to find the distance between this point and the line which is given with this vector parametric equation. So here, remember, this is T. We wrote this before, like TA plus B. And this would be R of T. So if this is the equation of the line, then this is the point this is the given point on the line, or a given point on the line. So this is, we can say that's a point on the line. And we can say that this is the vector, we called it A before, that was parallel to the line. So they say from this equation, we can read off a point B, this one, and a vector A parallel, namely this one. Using figure 1.76, the length of the vector BP0 minus this provides the desired distance from P0 to the line. Because BP0 is here, and if we subtract the projection onto this line, then we get this distance here, we get this vector here. We've done that many, many times. That is, if we take this vector minus this vector, we get a vector that starts here and moves in this direction to here. So if we take the magnitude of that, that's going to be the length. So we can just do that. So we have to write what BP0 is. That's here. So we already said that B was here, and we were given P0, so we need to subtract this from this, or the other way around. So we take 213 minus this one. We get this. So that's BP0. That's here. It's this vector. Now we have to get the projection of this onto here. So that's the projection of BP0. That's this part onto A. And we take this formula that we showed before, and it says A dot BP0 over A dot A times A. So this thing works out to be a scalar because it's a dot product over a dot product. So it's a multiple of A. So it's going to be actually this multiple of A to here. And we do all of this, and we multiply times A, and this is what we get. So the desired distance is this minus that and the norm of that. So at the norm of this minus that, which gives us that. And if we get the norm of that, remember, how do we get the norm? The norm is going to be the square root of this dot itself. So when we dot this times itself, we get 4 plus 1 is 5. And then we have to take the square root, so we get the square root of 5. So finally, we got the distance, D, here. Right, that's one way. The second way involves some trigonometry, and I'm not going to cover that one. But presumably, we're going to get the same. Actually, we run into this still, apparently. Anyway, we still get the same answer, so you can check that yourself. Let's go on to the next one, which is the distance between parallel planes. Okay, let's next do the distance between parallel planes. So we have two parallel planes, and we want to find the distance, which is, I guess, the shortest distance between the two planes. So they say, take, for example, this plane and this plane. So we have to make sure that they're parallel, otherwise the shortest distance is 0, I guess. But anyway, we're only working with parallel planes. So how can we know that these are parallel? Well, they say because if you look at, we can read off the normal here, and it's the same normal here. So they both have the same normal. So they're both parallel, but they're not the same planes. So using figure 1.78, this figure here, we can see that the desired distance here is given by the projection of this onto the normal. Right, so we can write it by P1, P2 onto the normal, where P1 is a point on in plane 1, and P2 is a point on plane 2. And n is a vector which is normal to both planes. First, the vector n that is normal to both planes can be read off here. And so we get this. It's not hard to find a point on P1. On a plane, a point P1 on this plane, because we have this plane's equation. So we can just take y and z equal to, x and y equal to 0 and solve for z. So we get something like this, and we can do the same thing to get something like this for P2 in this plane. And so we can then write P1, P2 as this, I guess. Remember, we take P2 minus P1, so we get 20 minus 5, so we get 15 here and 0 elsewhere. Now we can calculate the projection onto n by using this formula. So it's n dot this in the direction of n, or times n. So we get all of this, we get this, we get this. And then we just want the magnitude of this for the distance. So we look at the magnitude of this, which means, again, we take the dot product with itself and then take the square root. So it's going to be the dot product, just this part. And I guess gives you 9. And then you can take this out. So you get this, which is, I guess, square root of 9 is 3. So you get 5. Now the distance between two skew lines. So you have two skew lines. That means you think. I guess you have to think about the plane that a plane that this one lies in, and a plane that this one lies in, that don't intersect. And once you obtain those planes, then the distance between this line and this line is the distance between the two planes. So we already figured out how to find the distance between two planes. So I guess we just need to find the two planes, non-intersecting planes. So here they give us one line's equation in vector form. Remember, again, this is the r. We usually write this as r, and we usually write this as a, and we usually write this as b, and the same thing here. So I'm sorry, maybe we don't need to find this plane and this plane. We're just going to take a point B on point B on line 1, and B1 on line 1, and B2 on line 2. And we're going to